Hello students, let me ask you something simple. When you say, I walked a long distance today, what do you really mean by distance? Or when someone says, the car accelerated suddenly, how do we define that word acceleration scientifically? In daily life, we use such words casually, but in physics, we need precise definitions. That's because motion is a universal phenomenon, and to study it properly we must have universally accepted terms. That is why concepts like distance, displacement, speed, velocity, and acceleration form the very foundation of kinematics. In this lesson, we will carefully understand each of these definitions with formulas and examples. Let's begin with the most basic terms, distance and displacement. Distance is the total length of the actual path traveled by an object. It is a scalar quantity, which means it has only magnitude, never direction. On the other hand, displacement is defined as the shortest straight-line distance between the initial position and the final position of an object. Displacement is a vector, which means it has both magnitude and direction. For example, if you walk 3 kilometers east and then 4 kilometers north, the distance you traveled is 7 kilometers. But your displacement is only 5 kilometers in the northeast direction because that is the straight line from start to finish. Mathematically, displacement vector delta R equals R2 minus R1. Now let's talk about speed and velocity. Speed is the rate of change of distance with time. Being scalar, it is always positive. The formula is speed equals distance divided by time. In contrast, velocity is the rate of change of displacement with time. It is a vector quantity and can be positive, negative, or even zero depending on direction. The formula is V equals delta R divided by delta T. Suppose a car moves 100 meters north in 20 seconds. Its speed is 5 meters per second and its velocity is also 5 meters per second north. Notice the difference, speed only tells us how fast, while velocity tells us how fast and in which direction.
Next comes acceleration. Acceleration measures how velocity changes with time. Formally, it is the rate of change of velocity per unit time. The formula is A equals delta V divided by delta T. Since velocity itself is a vector, acceleration is also a vector. For example, if a car's velocity increases from 10 meters per second to 20 meters per second in 5 seconds, then acceleration equals open bracket 20 minus 10 close bracket divided by 5, giving 2 meters per second squared. On a velocity time graph, this appears as the slope of the graph. If the slope is constant, acceleration is uniform. Now let's classify motion as uniform or non-uniform. In uniform motion, an object covers equal distances in equal intervals of time. Its velocity remains constant and acceleration is zero. In non-uniform motion, the distances covered in equal intervals of time are unequal, meaning velocity keeps changing. For example, a satellite orbiting Earth at constant speed is in uniform motion, while a car driving in city traffic is in non-uniform motion. Graphically, uniform motion shows a straight line in distance-time graphs, while non-uniform motion shows curves that keep changing slope. Let's apply all these definitions in a numerical example. Suppose a particle moves 3 kilometers east and then 4 kilometers north in 2 hours. Step 1. The total distance traveled is 3 plus 4, which is 7 kilometers. Step 2. Displacement is the shortest straight line path, which is the square root of 3 squared plus 4 squared, giving 5 kilometers northeast. Step 3. Average speed is distance divided by time, so 7 divided by 2, which is 3.5 kilometers per hour. Step 4. Average velocity is displacement divided by time, so 5 divided by 2 equal to 2.5 kilometers per hour in the northeast direction. This example shows how speed and velocity can have different values for the same motion. So let's summarize what we've learned. To describe motion, physics uses clear definitions: distance, displacement, speed, velocity, and acceleration. Distance and speed are scalars. while displacement and velocity are vectors. Acceleration tells us how quickly velocity changes with time. Motion may be uniform when velocity is constant, or non-uniform when velocity varies. And through a simple example, we saw how these quantities are calculated and distinguished. These basic definitions are the very building blocks of kinematics. Without them, we cannot move to more advanced concepts like equations of motion, projectile motion, or relative velocity. I hope today's session has given you a crystal clear idea of these fundamental terms. In our next lesson, we'll continue building on this foundation to explore deeper aspects of motion. Until then, keep observing the world around you, because every moving thing is a live example of physics in action.